This opportunity, and whole IAPNEOCON team for giving me this opportunity. We will be having practical sessions on 30th August at Kalinga Institute of Medical Sciences, Bhubaneswar. And today we are going to start with online lectures. The hands-on will be there on 30th August. So this is the first online lecture on basics of overview and basics of echocardiography. And the importance already Dr. Mohit has that discussed that this forms the building blocks of understanding the what echocardiography, what information and neonatologist or pediatrician is likely to derive from the echocardiography. So I will be discussing the physics of ultrasound, a little bit, the basic principles of the ultrasound physiology, how they are going to be applied in the clinical day-to-day clinical practice. Of course, we will be applying these principles when we interrogate hemodynamically unstable baby or PDA or PPHN or other important scenarios. But the basic principles, they do remain same, whether it is an ultrasound, whether it is an echocardiography. So I'll be discussing how to optimize the image and how to understand the physics of the ultrasound to optimize our image so that we can get best out of these images. We'll be discussing various modes which we can use to interrogate the heart and get the information from the point of care ultrasound on echocardiography. We'll be discussing the clinical utilization and caveats of those various modes. So let's kickstart. So the first thing is the learning about how the ultrasound waves are produced. So this is a schematic diagram of an ultrasound transducer. So this whole is ultrasound transducer. The ultrasound machine, this is connected by the ultrasound transducer with the help of cord. So the ultrasound machines that produces the electrical signal. This electrical signal go to the ultrasound probe this is the footprint of the ultrasound probe where the piezoelectric crystals are placed side by side. This electrical current is going to stimulate the piezoelectric crystals and they produce ultrasound waves. So we know that in the day-to-day, conversation, the audible frequency is below 20,000 hertz or 20 kilohertz. But ultrasound waves are way higher in the frequency. They start with something like 2 megahertz and go all the way to 15 megahertz and even beyond. So these waves, ultrasound waves, are produced and they are transmitted to the organ of interest. May I request the participants to kindly mute themselves? Please stay muted. If you have any doubts, any questions, you can put in the chat box and we can take them at the end of the lecture. So once these ultrasound waves hit the target and come back, they approach this transducer once again, and this transducer detects these reflected ultrasound waves, and it produces current, and this current goes to ultrasound machine and it processes the information and try to project it on the screen, which we see on the in the form of 2D color Doppler and etc. etc. So this is how the ultrasound machine works. The second thing is what about these properties of these ultrasound waves? So these ultrasound waves have a relatively constant speed. Yeah, I may say. So they in the body tissue, majority of them are in solid or liquid. So the speed of the ultrasound waves inside the body tissues are roughly 1500 to 1600 meter per second, depending upon how dense are the tissues. The more dense are the tissues, the more is the speed of ultrasound waves inside the tissues. It is important that ultrasound wave, they make a two-way trip. They go inside, hit the target, and come back. So all ultrasound beams, they make a two-way trip, and all distances are thus calculated in such a way that they to and fro distance is machine understand that the beam has gone, struck the target and came back. So, and the time and distance are accordingly calculated. They are halved. The deeper are the tissues or anatomy, I mean the areas of deeper are the areas of interest inside the body, the longer it will take for ultrasound to go and come back. And it is, this algorithm is inbuilt uh, inside the machine. So machine understand depending upon, and we'll shortly discuss the formula. So machine understand that what is the time taken, what is the, and it knows the speed of the ultrasound wave, and thus calculates the distance between the transducer and the object of interest. So once the ultrasound beam approaches a particular uh, anatomical organ or tissue, then there can be three fates. One, it can transmit through it. The second, it can get reflected, as is shown in the figure. And third is it can get scattered. So it depends upon, it is an absolutely smooth surface, it will come and get reflected as if the light is getting reflected. And if it all depends upon how pervious is the structure to these ultrasound waves. So if so they can get transmitted, they can get reflected, or if the surface is irregular, they can get scattered throughout. So the reflection or refraction, that depends upon the acoustic impedance, the property of the tissue, that is acoustic impedance. It is the impedance, it is the resistance offered by the tissue to the ultrasound waves. So ultrasound waves come, they depending upon the impedance, depending upon the resistance which this tissue offers to these ultrasound waves, it can get partially get transmitted and partially get reflected and scattered. So if the tissues, so generally in the body, you will encounter the different tissues with different acoustic impedance. So for example, there could be a wall of the heart and another wall of the heart, and in between the heart, there is blood. So blood has a different acoustic impedance and the wall has different acoustic impedance. So when these two are in contact with each other, there is a smooth and long tissue surface which has a differential acoustic impedance, to which the waves can partially transmit, partially get reflected, partially get distracted, scattered. Generally, in the body tissue, they are not absolutely smooth. If they are absolutely smooth, majority of them get either transmitted or reflected. But as they are not absolutely smooth, they are little, rough surface of interface between the two tissues. The majority of them, they get either transmitted or scattered. Some will get reflected. So this degree of mismatch is directly proportional to the larger is the degree of the mismatch, the larger is the scatter or larger is the reflection. And lesser is the degree of mismatch, the more is the transmission. Lesser is the reflection, lesser is the scatter. As I said previously, more irregular or more inhomogeneous interfaces, they do scatter a lot of ultrasound waves, and they appear as echo signals. Okay. So this is how the ultrasound waves once they go inside. So once they go inside, they transmit and as they enter into deeper and deeper structures, they do so. They encounter some tissues here. Some of them get reflected, some get refracted, some get transmitted. So we can understand that some get scattered here, some get scattered here. So as these waves penetrate down, go down and down, there is a loss of signal and there is attenuation. This is known as attenuation. So you get all black signals because there are very less signals which are going at the bottom of as you penetrate deeper and deeper inside the tissues. There are ways to overcome that. We'll discuss shortly. Okay. Now the second concept is the wavelength and frequency. Okay. So this is consider this is a wave. These are two waves. This is a pulse consisted of two waves. So one is this is the positive deflection, negative deflection. Here is the one wave, and here is the second one. So this is the wavelength from beginning to the end of first wave is the wavelength. Okay. So what is the frequency? The frequency is 1 divided by the how of the I mean the is inversely proportional to the wavelength. The frequency and wavelength, they are inversely proportional. So number of waves per second is known as frequency. So this is wavelength. The other property of the physical attribute is amplitude. So this particular wave has got a certain amplitude, and once the positive reflection and negative reflection are increased, their amplitude or energy is higher. So we will be dealing with majority of the time, we will be dealing with frequency and wavelength, and they are important to understand because the wavelength is responsible for penetration. So larger is the wavelength, the larger is the penetration. So if we want to interrogate deeper structure, we want to include or we want to use this transducer which throw ultrasound beams with a greater wavelength. Once we interrogate, but the downside of this is the deeper penetration, the downside is that they have lesser frequency. And once they have lesser frequency, we know that these structures are not that well represented on the screen, or in other way, in other words, they have a lesser resolution. We'll discuss the resolution shortly. So to overcome that, you need the ultrasound waves with higher frequency. So if you want to interrogate the superficial structures, we want ultrasound with a higher frequency. And if you want to interrogate deeper structure, we want an ultrasound with the larger wavelength and consecutively lesser frequency. Okay, so this is the distance. This is how the machine calculates the distance. The distance is equal to c multiplied by t. C is the speed of the light multiplied by the time it takes, and machine divides it by 2. The machine knows that that speed of the light of the ultrasound wave is 1540 meter per second, and machine understands and knows what is the time. So as soon as the machine emits the signal, it goes, hits target, and comes back. The machine knows what is the exact time in this to and fro motion, and then machine uses this formula to understand how deep is the structure from the transducer. The relation between the frequency and wavelength and speed of the sound and period that we have discussed, that the delta, which is the wavelength, is equal to speed of the light divided by the frequency. So it is inversely proportional to the frequency. So we have previously discussed in the previous slide the importance of this. So if we want to have improved resolution or see the images in a better way, we want a higher frequency probes. And higher is the frequency, the lower is the wavelength, and thus the penetration is compromised. So we have a trade-off once we use this trade-off to optimize the image. Okay. So for optimizing image, we need various physical attributes. One is frequency that we have discussed. Another is depth. So how to set up the depth of the sector when we are interrogating the heart or any other anatomical structure using ultrasound. We'll discuss shortly. We will discuss about the resolutions, various types of resolutions, and how to. So there are basically 3 types of resolution: axial resolution, lateral resolution, and temporal resolution. And we will discuss them one by one. We will study the importance of focus and the sector width in improving these resolutions. We will discuss about we have discussed about the attenuation. We will discuss about how to overcome this attenuation by post-processing of the signals which are coming from the tissues, and which is also known as gain or time gain compensation. We will discuss about them, and I can discuss a little bit about harmonics also. So first is depth. So what is the depth? So suppose I want to interrogate the this. So this is a apical four-chamber view. Many of you might be knowing, but those who don't know, I will orient you to this. So this is a parasternal long axis view, and this is this particular view shows the wall of the right ventricle, the interventricular septum, aorta, lateral ventricle, left ventricle, left ventricle, the mitral valve, and left atrium. So basically, this is the view. This view is used to study the movement of mitral valve, the movement of aortic valve, the aortic dimensions, the ventricular diameters, left ventricular diameters in diastole and systole, and various indices associated with these measurements. So if we want to study the any particular object, say for example, if you want to study the left ventricular diameter. So now left ventricular diameter is only this much. Okay? But this area, you can understand that this is the pericardium, and this area is practically useless. We are wasting the screen. So what we can do is we should optimize the depth so that our anatomical area of interest. So this is the left ventricle, occupies at least 2/3 of the screen. Okay, we should not waste. This gives a much better view of the heart, much better view of this anterior mitral leaflet and posterior mitral leaflet, and this improves our ability to measure or understand the information from these images. Again, one more example. This is a short axis parasternal view where we are interrogating the heart, left ventricle, in a cross section. This is the left ventricle and this is the right ventricle. So this left ventricle is appearing, you can see, very small, and this part is practically useless. So once we improve the depth, increase the depth, we can see that the left ventricle is now visible in a much better way, and right ventricle is also visible in a much better way. Whereas here we are not able to see the right ventricle. So this is importance of adjusting the depth, and we can see that our area of interest is practically occupying roughly 2/3 of the upper part of the screen. Now coming to resolution, I have discussed that there are various types of resolutions. We will discuss about the contrast resolution, where we will deal about the attenuation and gain associated with it. But in this section, we will first deal about the detailed resolution. The detailed resolution deals with the ability of the ultrasound to identify the details of the anatomical structure. So identify two separate objects as two separate objects. Okay. So there are two types of the detailed resolutions. One is axial resolution and another is lateral resolution. The axial resolution is when the objects are lying in the line of the beam, and lateral resolution is when the objects are lying perpendicular to the beam. So beam is going this way and the objects are lying like this. And in axial resolution, the objects are lying in the line of beam. The contrast resolution and the temporal resolution deals with the moving structures. So when the structures are moving, say for example, the aortic valve is moving, say mitral valve is moving, say blood is moving. So that kind of ability to detect the motion of these structure and various indices associated with them deals with the temporal resolution. And let's discuss them one by one. So the axial resolution discriminate the target along the, I have discussed that the target is lying, these two separate objects, they are lying along the scan line or parallel to the scan line. Okay. So let's discuss this schematic diagram to understand what do I mean by axial resolution. So they are the two objects. One object is this, another is this. And let's say the ultrasound emits a signal. So now ultrasound emits beam, the transducer emits this signal. This is the wavelength. This is second wave, this third wave, and so on. So it hits the target and comes back. It hits the second target and comes back. So you can understand that these two, both of these targets, they are lying in the same wave. So, okay. So this is the same wave starting from here to here or starting from here to here. So this is the same wave. They are lying in the same wave. So once this wave hits this target and comes back and again hits this target and come back, practically the same, the transducer understand that this is the same wave which is hitting this, and with it takes both these objects as a single object. It will not discriminate in both these objects, between both these objects. In contrast, when we use an ultrasound probe with a higher frequency, okay, they do fall in the different waves, and thus this wave will hit the first object and comes back, and the second object and the come back in the two consecutive waves. When the two consecutive waves is hitting and coming back, then the ultrasound transducer will so the machine will take them as two different objects. So what is the bottom line? The bottom line is that there is the higher the frequency, the better is the axial resolution. And I have discussed that there is a trade-off between resolution and penetration. So if we want to increase, the moment we try to increase our frequency, we increase our axial resolution and we compromise on the penetration, because now with higher frequency, the waves will not penetrate so deeply. Okay. So for this reason, because of the neonatal structure are small and they are closer to the skin as compared to the adults, so we use relatively higher frequency probes in neonatology. Generally, they range between say 4 to 12 megahertz when we are interrogating the neonatal heart. The second is the lateral resolution. Now, this is the ability of discriminate two close objects which are lying perpendicular to the scan line. And let me, with this schematic diagram, we know that the ultrasound beam are going in this direction, and these two objects are lying to the perpendicular to the ultrasound beam. So if we so this beam is going, and it is hitting both these structures are coming in the same beam, and if the amplitude are little different, they may consider them, these two structures, as a separate structures. However, the amplitude is fixed. So what do we do to improve the lateral resolution? Furthermore, this problem with the lateral resolution that comes very I mean in a particularly with the phased array probes, because we know that in neonatal heart the ribs are very close, the footprint of the probe is very small. So when the waves go inside, they diverge, and because as they diverge, the density of the waves they decrease, and when the structures are in deeper planes, then the lateral resolution is going to be lesser. So what's the way out? The way out is the focus of the ultrasound beam. So the machine comes with the modern machines, they come with the an additional feature, that is the focus. So what is the focus? The focus is so there is depending upon the focus divides them into near field and the far field. So the ultrasound beam, they converge towards focus and then they diverge. Okay. And the second way, and I'll show you how it is done. So this is the phased sector of the phased array probe, and this is again our parasternal long axis view, where it is right ventricle, left ventricle, the mitral mitral valve and the aortic valve. And you can see that this is the depth. Say this is 5 centimeter. Along this depth, there is something, along this depth is something known as focus. So this is the focus. Now, by adjusting this focus up and down, we are asking the machine to decide which is the maximum at the point where the machine is likely to have the maximum resolution or maximum convergence of the waves. So if suppose your area of interest is your aortic valve, then you can adjust your focus so that the focus is somewhere here. And if the area of interest is mitral valve, uh, and you are not able to see, if you are able to see, then it's fine. If you're not able to see, then you can adjust, and you can see that the mitral valve are very nicely depicted as compared to the aortic valve. And it's because the focus is adjusted in a way that it is paralleling the mitral valve. So that's the importance of the. So there are two ways to improve the lateral resolution, as said. The first is that you improve the frequency. With higher frequency, you improve lateral resolution. And the second is that you use the focus to improve your lateral resolution. The third is the temporal resolution. And as I said that it improves the ability of the uh, uh, to detect the object if it is moving over the time. So suppose an object is moved from A area to B area, the ability of the machine to detect this motion of of the object is the temporal resolution. If the temporal resolution is very good, then the movement of this particular object, it appears smooth. And if the temporal resolution is low, then it appears, a rough movement. We see the rough movement of the object. So it is synonymous with temporal resolution improves with the pulse repetition frequency, and it is synonymous with the frame rate. So what is the frame rate? The frame rate is so every beam that goes inside and it penetrates the frame, comes back. So the time one ultrasound beams takes to scan a frame is the one frame, time for one frame. And if you divide this by one, I mean 1 divided by time to scan one frame is the frame. So higher is the frame rate, more number of images they are getting stored inside the machine. They are captured and stored inside the machine, and more are the number of images stored in the unit time. That is the that machine has improved frame rate, and more are the pulses. So the once the pulse goes inside, it comes back. It is one pulse cycle. It again a pulse goes and comes back. It is a second pulse cycle. So the number of pulses which are repeatedly over a unit time is the pulse repetition frequency. Suppose a machine sends say 30 megahertz, so 30,000 pulses per second, then it is the pulse repetition frequency of that machine. So they are almost synonymous, not exactly same, but they are synonymous. So the time to scan one frame is the pulse repetition period into the number of scan lines divided by the frame. Okay. So higher is the frame rate, higher the pulse repetition frequency, the better is the temporal resolution. So how we can improve the frame rate? So decrease depth. If we decrease the depth of the structure, there will be more number of pulses. The speed is same. The pulses go inside, come back. So they make a trip faster, and once they make the trip faster, the more frame rates are the ultrasound beam is able to have a more frame rates per unit time. So because of that, the temporal resolution is going to increase. So one way is to decrease the depth. The second way is to improve the pulse repetition frequency. If you're sending, say, if your pulse repetition frequency is X, and if you make it 2X, then automatically your temporal resolution is going to be higher. The third is the sector width. So if we are having this big sector, then we have 1 wave, 2 wave, 3 wave, 4 wave, 5, 6, 7, and so on. So several, millions of waves are required to scan this sector. If we decrease that has their own frame rate. So once you narrow the sector, now lesser number of waves will be needed to scan this frame, and therefore there will be decreased time required to scan the whole frame. So therefore the frame rate will increase, and therefore the temporal resolution will increase. So you'll see while doing this ultrasound or echocardiographic interrogation of particular area, say for example, you want to know the speed of blood across the aortic valve. So you narrow the sector width, and that will improve your temporal resolution. That will improve your ability to detect the motion of this particular tissue or particular uh, uh, of the blood or organ of interest. Okay, so we will discuss about various modes, but M mode has a higher, is associated with higher pulse repetition frequency and thus has better temporal resolution as compared to the 2D. Okay. Now we have discussed the temporal resolution and the lateral resolution and axial resolution. Now we'll discuss the contrast resolution. So we have discussed previously that once the ultrasound beams are going inside, they are hitting the targets, they are getting scattered or reflected. And as they are going down and down, the less and less waves are available, less and less ultrasound waves are coming back, and there is attenuation. And all of the area is looking black. Now, one way to how we'll improve the resolution. So the resolution is very less in the deeper structures. So how we'll increase? We'll improve the gain. What does gain do? So as the lesser number of waves are coming back, these waves are enhanced by the machine, which is the post-processing post-signal processing. I mean, we are not doing anything once we are sending the signals back. We are just picking the signal which is coming back from the tissues, and we are enhancing those signals, and that gives you a better contrast, and which is known as 2D gain. So say this is the structure. You have there was an attenuation. We have increased the improve the 2D, increase the 2D gain. Now these structures are appearing better than what they were appearing before. But the downside is that you can see that there is noise. There is noise inside the ventricular cavity. Now this ventricular cavity. So by the way, this is long axis parasternal view again, and this is the M mode line. And again, this is the motion of the right ventricular wall, interventricular septum, and posterior ventricular wall is depicted on the XY plane. So this particular the anatomical organs to which this line is cutting are depicted on this frame. So you can see that the ventricular cavity should not have this dot line. So this is known as noise. So it increases 2D gain. Once we increase the gain, it improves all the signals. So you can see that the signals which are close to the structure, they are highlighted much more than the structure which are deeper down. And you can see that the noise will start appearing if your 2D gain is very high. So you need to adjust in such a way that you increase the gain to a point when your noise does not start appearing inside the ultrasound images. Okay, again the example. So this was the structure which was having attenuation. We increase the gain. Now these deeper structure, they are appearing much better, but look at this structure. There's a lot of noise which has started appearing, and look at this. Again, there is a lot of noise. So to overcome this problem, we can have a differential gain along the line. Okay, so we have, say, many buttons, and they increase the gain. So they divide the whole of the sector in proportion. I mean, they make different sector proportion to the number of buttons available. So for example, here 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 buttons are available. So divide the this sector into 8 8 equal zones, and then I know that I don't need so much compensation here. So my gain will be lesser on the top, and I know that as I go down the line, I need more and more gain. So the structure which are deeper down, I will adjust my gain so that they have more gain. So this is known as the time gain compensation. And it now these structures are appearing in a much better way. They are appearing in a much better way as compared to the 2D gain, which was increasing the gain in equal proportion. But here we are uh, increasing the gain according to the region of interest. So that is time gain compensation. Again, another example. So this is the time gain compensation. We have the closer areas and the farther areas, they have differential gains. And then now this image is appearing in a much better way without any noise. Okay. So after this, let's learn what are the various transducers. So there are mainly three types of transducers. One is sector probe or phased array probe. Another is linear probe and another is curved probe. Almost every machine they come with these three types of probes. They have their own advantages and disadvantages. These two have very big footprints. So you know that these are the two ribs. So this is the footprint of this probe. So we know that majority of the waves are obstructed, and uh, the second thing to note is that they have a rectangular sector which appears on the screen. So this is the sector which appears on the screen when the linear array probe in the linear array probe. It is generally used for very high frequency uh, the measurements which require very high frequency, for example, 12, 10 to 15 megahertz. Typically, the structures which are very superficial to the skin. For example, you want to see study this any artery which is very close, say radial artery, then you use the linear probe. Another is curved probe, which is also having a very wide footprint. But then these rays diverge as they leave the footprint. It is called a curved footprint. In neonatology, we use the sector probes. The curved are required. For example, if you are interrogating the brain, and we have to put the curved probe on the on the anterior fontanel, so that the waves diverge and we get the whole idea of the inside the brain of the baby. Or similarly, if you want to scan the abdomen, then we use the curved probes. Now we know that in the neonate, the ribs are very crowded, and we get a very small area through which we have to interrogate the heart, and essentially many anatomical areas of interest. So we use the sector probes or the phase array. Here the footprint is small, and the ultrasound waves, they originate and they diverge and they do as they go inside. So that is the advantage, that we are able to send a lot of ultrasound waves as we go inside, but the downside is they diverge and we lose out on the lateral resolution. But we have discussed how to improve the lateral resolution previously. So these are the sectors which are, so phased array probe has a triangular sector, as we were discussing previously. The linear has a rectangular sector, and the curved array has got a mixture of these two. So let us now discuss the various modes which are available. So we have 2D mode, M mode, and Doppler. So we will be discussing them one by one. In 2D, it is two-dimensional. It has got an x-axis and a y-axis. So once the ultrasound beam, which has got one axis, y-axis, and x-axis, it goes inside. It cuts the anatomical area in a way that it depicts the area in an XY plane. So this is the XY plane. So this is the left ventricle. So this is the left ventricle, and this is the right. This is the right ventricle. This is the left ventricle, and this is the right atrium. So once it is cutting the heart through and through, the heart is appearing in a way that this is the left ventricle, left atrium, right ventricle, and we see this type of structure on the screen. So this is 2D, two-dimensional image. What is M mode? The M mode is the motion mode. It is also known as motion mode. When the ultrasound beams are sent along a single line in the anatomical area of interest. So this is the same view which I have been discussing previously. So this is left ventricle, this is interventricular septum, this is a posterior wall, this is mitral valve. So this line is cutting through the right ventricle, interventricular septum, mitral leaflets, and posterior wall. And this line is cutting these structures at this particular point, only at this point, only at the tip of mitral valve, only at the tip and at the posterior wall at a particular point. Now, this particular point, the motion of the interventricular septum at this point is depicted here. So it is not picking up the motion here, 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 here. No, not. It is picking up the movement of this interventricular septum only at this point. Similarly, at the tip of mitral valve, at the tip of mitral valve. So this motion is depicted here. So say this is the interventricular septum. This is the anterior mitral leaflet. This is the posterior mitral leaflet, and this is the posterior. So this is the beauty of this M mode, that it picks up the motion of these structures along a single point, and it has got a very high pulse repetition frequency, so very good temporal resolution, and hence the measurements which you can get from 2D images, the M mode images, are way better, far better than the dimensions which you get, corresponding dimensions which you get from 2D images. So we get from leading to leading. Previously we used to do from the leading edge to leading edge, but right now the machines have got a better resolution. So we measure from the inner edge. So this is the inner edge. Okay, this is the inner edge. So every structure has got this line. Say for example, this line has got an upper end and lower end. So upper is leading, lower end inner edge. So we got from inner edge to inner edge. Okay, and we need to align the structure to get the best resolution. We need to align the structure in such a way that the structure, the area of interest, is exactly perpendicular to this line. If it is not perpendicular, then our measurements are likely to be erroneous. And there should be clear points in the cardiac cycle where we need to put this line. For example, I want to measure the movements of the tips of mitral valve. So I need to put this M mode at the tips of mitral. So these are the three things we need to remember while using the M mode. So this M mode is used in various applications. You must have heard that how to calculate the fractional shortening. So if we put these M mode at the tip of the mitral valve, we measure the maximum diameter or the end diastolic diameter and end systolic diameter, and we can get the fractional shortening. You must have heard about the LAAO ratio. So many observations, they are done by help of M mode, which are of interest while evaluating while doing the various evaluation. For example, hemodynamically significant PD, for example, knowing the systolic function, which we'll discuss subsequently in the subsequent later lectures. So let's now discuss the very important concept about the Doppler ultrasound. So might have, everybody must have experienced while standing on the, railway platform, as the train approaches us, the siren, and it blows the siren. There is the siren has got a particular intensity, but as the train approaches towards us, the intensity increases, and as the train goes away from us, the intensity of the signal decreases. And this is because of the Doppler effect. So what is Doppler effect? We understand with the help of a schematic diagram. So suppose this is the ultrasound transducer, and this is the object of interest. In this object, I have depicted one RBC. So the machine is going to throw a ultrasound beam, which has got a certain frequency, which is depicted as transmitted frequency, or FT. Now this object, this beam has hit the object and it has come back with a certain frequency, which is the FR, okay, return frequency, which is returned. So if the object is stationary, now the frequency I'm sorry, kindly mute yourselves. Participants, kindly mute yourself. So the transmitted, if this object is stationary, the transmitted frequency is equal to the frequency which has returned from the after hitting this object. So Ft is equal to F1. So in another example, this object was moving, and now the transmitted frequency has hit this object, and this movement has and it has returned. Now, what do you think? The transmitted frequency, the frequency which has returned should be equal to the transmitted frequency or no? So it is intuitive to understand that no, because there was some energy associated with the movement of this object. Now the frequency which has hit this object has gained some more frequency, and now the frequency which has returned is likely to be having a higher frequency than the transmitted frequency. So if the object was moving towards the transducer, then first of all, what is the Doppler shift? Now the Doppler shift is the difference in the frequency from the frequency which has returned, and if we deduct the transmitted frequency from the frequency which has returned, this is the Doppler shift. And if the frequency of the returned signal was higher than the transmitted frequency, then this is a positive Doppler shift. And if the frequency of the returned signal was lower than the transmitted frequency, then it is a negative Doppler shift. So if the object is moving towards the transducer, the energy of this is likely to be higher, and it results in a positive Doppler shift. If the movement of the object was away from the transducer, this transmitted signal is going to lose some frequency, and this is known as the negative Doppler shift. Now, what is the application of this Doppler shift? Now we'll discuss three types of Dopplers. One is pulse wave Doppler, continuous Doppler, and the color Doppler. And we will discuss the fine variations of these Doppler applications, and we will discuss the caveats associated with them. So before that, this is the formula which the machine uses. So the Doppler shift is equal to twice the transmitted frequency multiplied by the velocity of this object divided by the speed of the ultrasound wave. So the speed, we know that it is 1540 meter per second. The transmitted frequency is known because we have fed this frequency in the system. The Doppler shift is known. The machine calculates the Doppler shift because it also it gets the it knows what is the frequency transmitted, it knows what is the frequency received, and it subtracts these two and knows what is Doppler shift. So the Doppler shift is known, the transmitted frequency is known, the speed of the ultrasound beam is known. So the velocity of the object is calculated, and this becomes the formula. The velocity is equal to the reorientation of the formula. So this has got application, because if we want to know what is the speed of the blood, we can know the speed of the blood by applying these principles of Doppler shift. Okay. Now there is one more issue associated once this object is moving inside the body. So in the previous example, the blood was moving towards the object, but it is possible the blood is moving little at the angle of this ultrasound beam. So what will happen? So if this object is moving in this direction and the transmitted frequency will be different from the received frequency will be different from the transmitted frequency, but then the motion was not in line with this transmitted frequency. So what will happen? So there will be an angle which has come into operation now. And this angle, the machine knows this angle, and machine automatically that puts I mean I'm sorry, the machine does not know this angle. Machine only understands the transmitted frequency and the received frequency. Machine knows that it has hit the object and the frequency has come back, and will calculate the Doppler shift. But because the cos theta is because the angle was there between the motion of the object and the ultrasound beam, then the relationship is now no longer V oblique C, but the relationship becomes V cos theta oblique C. Now cos theta we know is cos 0 is 1 and cos 90 is 0. So once, if the object is, so what is the application of this? So bottom line is that if object is moving towards the ultrasound, in line with the ultrasound beam, towards or away, so then cos theta is, cos 0 is 1. So then the Doppler shift will be maximum. However, if the object is moving in an angle, at an angle, for example, if the object is moving exactly perpendicular to this, then the cos 90 is 0. And if we apply here, this becomes 0. And once it is multiplied, everything becomes 0. So machine will not perceive any signal. And if anything which is moving perpendicular to the line of ultrasound beam, the Doppler shift will not be calculated, and the machine will understand that there is no flow across the particular anatomical area. In fact, the flow is there, but machine will not be able to detect that flow. It is because of the this particular principle. So we know that cos theta is, as we increase the angle from 1 to 90, the value of cos increases, and thus the value, I mean the value of the cos increases, and thus the measurements is going to be more and more erroneous as we go towards 90. So there must be an acceptable limit till which we can increase the angle, and this limit is 20. So if we'll increase the so the angle between the motion of object or motion of the blood flow and the ultrasound beam. So motion of the blood flow and the ultrasound beam is 20-degree angle is permissible. If we increase the angle between these two more than 20-degree, then all the measurements are going to be erroneous, and more is the angle, the more erroneous is the measurement. Okay. So if we have to improve the Doppler frequency or the Doppler shift, there are various ways with which it can improve. The velocity, if it is directly proportional to the velocity, if we increase the velocity, we can increase the Doppler shift. The velocity is constant, so that is null and void. The beam is more aligned, so cos theta is, if the angle is more towards 0, the cos theta value is more towards 1, the Doppler shift is maximum. And if the higher frequency, the other option is to improve the higher frequency, the transmitted frequency, because the Doppler shift is directly proportional to the transmitted frequency, and speed of the sound is constant. Thus, there are only 3 ways to improve that, and the best way is to reduce the cos theta angle. Okay. Now, what about continuous wave Doppler? Now, the continuous wave Doppler, this is the first Doppler principle, the first type of Doppler which I am discussing. So machine is sending signal. This is the transmitted wave. This is the received wave. So there is overlap between these two waves. This is the received bundle, transmitted bundle in yellow, and red is received bundle, and there is an overlap, and the region of maximum overlap is the region of maximum Doppler shift. So it calculates the Doppler shift all along the line, and the maximum Doppler shift it picks up, and that it displays as the value. So this is the diagrammatic representation. So this is a transmitted signal, this is the received signal, and the machine calculates the product of these two, and it filters and smoothens it out. And this is the Doppler shift which the machine calculates, and this is the maximum Doppler shift which the machine calculates. So this is at particular area. There could be other Doppler shifts in various areas. So that machine picks up the maximum Doppler shifts and it depicts on the screen. So what is the application? The application is in Bernoulli's theorem. So suppose there is a very narrow area through which the blood is moving. So there is a particular pressure before, there is a particular pressure after, there is a particular velocity before, there is particularly velocity after this constriction. So then machines uses this formula and calculates the what is the pressure differences between these two, P2 minus P1. What is the difference of the pressure between these two? And practically V2, we know that the velocity of the signal is way higher after the constriction is way higher as compared to the velocity of the signal before. So it practically drops all the products associated with V1. So it calculates the Doppler shift. If we know the V2, we put our continuous wave Doppler here, and we align in such a way that it calculates the Doppler shifts here. And we know that what is the V, and if we know the V, we calculate the pressure gradient across this constriction. Let me give you an example. So this is the Doppler, this is the continuous wave Doppler which we have used at the level of tricuspid valve, and this is the TR jet. This is the ventricle, this is the atria. The blue colored signal is the tricuspid regurgitation inside the atria, and this is the continuous wave Doppler. This is the continuous wave Doppler. So it has given us the maximum Doppler shift, which is depicted as the pressure gradient across the right ventricle and right atrium is 75 millimeter of mercury. So how do we use this? So P1 P minus P2 is equal to 4V square. If you put this, so this was 4.3 meter per second. So if we put it 4.3 meter per second, this comes 74, and we round it off, it's 75. This is the same thing which the machine has calculated. And if we add right atrial pressure to it, because this is thrusting the flow of the blood inside the right atrium, if we add right atrial pressure, then the right ventricular systolic pressure is 75 plus this. This is the application which we use through continuous wave Doppler. Now, second is the pulse wave Doppler. So in pulse wave Doppler, suppose we want to calculate, we don't want Doppler shift all across this line. We want Doppler shift only at this point. Say this is the aortic valve only at this point. So the continuous wave, we know that it is calculating the Doppler shift all along. Now we want to calculate only at this line. So how do you do that? So we put on, so this is again the 4-chamber view. This is the left ventricle. This is the 5-chamber view. This is the left ventricle, right ventricle, and this is aorta. So left ventricular outflow tract and aorta. So we put our range gate, our sampling volume. This is the range gate is the sampling volume in which we calculate, we want to calculate our Doppler shifts. We want to calculate Doppler shift only here because we want to calculate the blood flow velocity only at the level of aortic valve. So when we want to calculate aortic valve, we put here, not here. So we want to put our range gate here, and we adjust the gate width so that it is reasonably within the boundaries of the aortic valve. And then the blood is sometimes the blood is at an angle. So we want to align our ultrasound beam so that the angle of the blood flow and angle between this ultrasound beam is less than 20. Okay. So the machine is going to calculate the Doppler shifts at this angle. Sometimes if the angles are not in, many times we are able to, adjust our align ultrasound beams so that they are in parallel to the flow of the blood. But if we are not able to do, sometimes we can use angle cursor. There are caveats associated with it, which is known as angle correction. We should not do it routinely. But if you are forced to do it, you can use some, but you need to give disclaimer because it will overestimate the the signals. So cutting the long story short, we want to know the Doppler shifts in this area in the range bit. So this is again the diagrammatic representation. So this pulse is thrown. This is a three-wave pulse which is thrown by the cursor, by the transducer, and this is the pulse 1 pulse, 2 pulse, 3 pulse, 4 pulse, which is hitting the area and coming back. So now the machine knows that okay, my beam was originally like that, and that it overlaps with this, and once it overlaps, it calculates some Doppler shift, and then it extrapolates rest of the Doppler shift. So one Doppler shift is calculated, another overlap, another shift is calculated, another is calculated, another is, and then it completes the hidden areas or uncalculated areas, and then makes a maximum. It assumes that the maximum Doppler shift could be somewhere here, could be somewhere like this. This is the maximum Doppler shift. So many times it assumes. So because of this, there can be loss in signal. So how can be loss in signal? So the pulse wave got because there could be loss of signal, so there is an upper limit of the Doppler shifts which the pulse wave Doppler can calculate. So basically the sampling frequency, the frequency with which the waves are sent inside, or pulse repetition frequency, is the frequency with which these waves are sent inside the tissue. So that should be more than twice of the signal frequency of the signal. So blood is coming from here. I am sending the volume of pulses. So the frequency of my sent signal should be more than twice of the velocity of the frequency of the signal which is coming from the other direction. If that is not the case, then there will be erroneous measurements. So my maximum Doppler shift will be ±2 of the pulse repetition frequency, and that is the Nyquist limit. If the frequency of the signal is more than that, more than the Nyquist limit, then there will be loss of signal. And why there will be loss of signal, I will discuss in this particular slide. So kindly pay attention. So suppose this is the pulse. These are the signal with which I am a signal frequency. The pulse repetition frequency. So 1 pulse, 2 pulse, 3 pulse, 4 pulse. So I am sending a volume of pulses inside. And this is the signal or the sampling frequency. The sample is, so blood is flowing with the particular frequency, and my Doppler shift is calculated by so here, and this is the sampled version of the Doppler shifts. So once I draw the line, this particular Doppler shifts closely matches the original signal. Okay. What will happen if this now I am sending the ultrasound wave with the same frequency, but the blood is having a very high frequency, much more than we saw in the previous slide. So now my Doppler shifts are calculated here, and accordingly they are represented here. This is represented here. This is represented here, and so on. And now the Doppler shifts are like this. So whereas it is way different than the original signal, and thus there is loss of signal in the sampled version, and thus there will be something known as aliasing. If my signal frequency is more than twice of my Nyquist of my pulse repetition frequency, which is the half of twice then the half of the pulse repetition frequency, which was my Nyquist limit. So this Doppler shift will appear like this. They will be broken and they will appear like this, and I'll show you how. So this is how. This is this is the systolic velocity. This is the diastolic velocity in the aorta, and if you see, or any particular artery, if you see, then this particular envelope is truncated here, and this the remaining version is appearing at the bottom of the slide, something like this. So this was the Nyquist limit of this particular signal. So what is the way out? the way out is okay. So how to handle this? I'm sorry. So how to handle this? So we can, the simplest is that we can increase the baseline shift. So if we increase the baseline shift, say for example, we increase the baseline shift from, so we depress this shift, the baseline down. So this such that this baseline comes at the bottom of the screen. Now this will start appearing, this will start appearing on the top, and we will be able to see the full envelope. But that is not the right way to do it, because although that is a cosmetically we can see the full envelope, but that is not the true a true Doppler shift, because the signal is getting lost. We are able to see because that is what is machine is calculating, but actually there is a loss of signal. So the best way is to increase the pulse repetition frequency. But pulse repetition frequency is constant for a particular probe. So what we'll do, we increase the scale. Once we increase the scale, indirectly it increases the pulse repetition frequency. So what we increase the scale, then what it does is it improves it increases the Nyquist limit, and then the signals are the true Doppler shifts are calculated. The other way is to decrease the Doppler frequency, which in odd case you can use, but the Doppler frequency is more or less constant. Although you can change it. There are ways to change it. Machine comes with an option, but that's not a very lucrative option either. So best option is to increase the scale. And second best option is, if we are not able to use the pulsed wave Doppler after making the scale maximum, then we use the continuous wave Doppler in that particular case. The last is the color Doppler. So we have known that the positive Doppler shifts are presented above the line. The negative Doppler shifts are presented below the line. Above, anything positive is depicted by red color, anything negative is depicted by blue color, and this is how the color Doppler is presented. So there is a scale. You can increase or decrease the scale depending upon the flow velocity. If you are dealing with venous blood, you want a very low scale, so you decrease the scale to 30 to 40. If your velocity is very high, you increase the scales to 60, 70, and even beyond if the frequency are very high. So how to optimize the image? For frequency, frequency if we increase the frequency, we have improved resolution, but then there is a decreased penetration and vice versa. If we reduce frequency, then we have increased penetration, and we can penetrate deeper structure, but with less resolution. So for depth, you adjust the depth so that your anatomical area occupy at least 2/3 of your screen, so that you have a better presentation of the better measurements of the anatomical areas of interest. Higher frequency gives a higher axial resolution, a higher lateral resolution, but it comes with a trade-off of penetration. For focus, it helps you improves your lateral resolution. If you decrease the sector width, then you improve your frame rate, and it helps with the temporal resolution. If you choose M mode, that will help the temporal resolution. If there is an attenuation, you can take help of gain and time gain compensation. We have discussed various modes. 2D, we use two-dimensional ultrasound to explore the anatomy. We use M mode to quantify the dynamic indices such as LAO ratio, the ejection, the fractional shortening, etc. And it has got a very good advantage in terms of improved temporal resolution. Thus, any measurement in M mode will be better than any measurement done in corresponding measurement in 2D. For continuous wave Doppler, it will calculate the maximum Doppler shift along the sampling line. There is no upper limit of Doppler shifts in continuous wave Doppler, and it is used to measure the pressure gradients across a very narrowed segments, such as tricuspid regurgitation, pulmonary regurgitation, and it is typically used when the flow velocity jets are higher than 2 meters per second, which are usually associated with a very high frequency. The pulse wave Doppler is used when we want to sample the velocity of a blood at a particular area. For example, an aortic valve, pulmonary valve, where we want to calculate the velocity of blood so as to calculate the left ventricular outflow or right ventricular outflow. We use range gate in that particular case. We study the flow patterns at that particular point, but it comes with the caveat of in form of Nyquist limit, beyond which the aliasing which happen, if the sampling frequency is more than Nyquist limit or the half pulse repetition frequency, then aliasing will happen, and you will have to improve your scale or convert to continuous wave Doppler in order to optimize your image. So I'll stop here. Thank you very much for listening to me, for being with me in this lecture. And if you have any questions, I'll be happy to. Dr. Mohit, please, over to you.
Arjit, are you there? Arjit? Sajan, really a good lecture. Okay, I am doing
Thank you, sir.
For last 30 years. I also gained something from
Oh, thank you so much, sir. It's an honor. It's an honor, sir.
I know. But once you are doing ultrasound for some time, then only you realize how important the basic things are.
That's true, sir.
That is there. So in the beginning, you don't realize all these things are useless. Or why should I know all these things? But once you really doing routinely the ultrasounds, and once you get into the problem, then then the knowledge of basic things that matters.
Yes. So I can't see any question in the chat box.
Questions are there, and Jagdish is also not there. So every day, Jagdish, any comment? He is a scientific committee head.
Yeah. No, I was there. I was listening to. Yeah. I joined late slightly.
Any comment?
I request all the participants to be attentive in the classes, because these classes, 8-9 classes, are very important. So that is the special request to all of you. Please don't expect that all the time we will send you the recordings and you will get the recording and learn from the recording. So because the doubt clearing can happen directly on when you talk to the faculty and discuss with them. So don't miss this opportunity. So thank you.
And also Jagdish,
yes,
is this webinar style is okay, or shall I convert this into the meeting?
No, this is okay, sir. I think the participants, anybody can tell.
In the webinar, participants can ask the question in the chat box.
Yes, sir.
In the meeting, they can directly ask the questions.
Yes, sir. Yes.
So which one is better? Because both the options are there in the Zoom. You can convert the webinar into the meeting also. But that the problem happens.
Meeting will be better, I think, sir.
Meeting
will be better, sir. I think.
But the problem in the meeting that of the disturbances.
Okay.
On the attended side, now if they don't keep them unmuted, then the problem happens because a lot of disturbances will come.
Yes, that I understand.
So I don't. Sajan, what do you say?
Sir, they have their advantages, disadvantages. So generally participants, they hesitate in this is the first lecture. I mean, generally we have seen participants hesitating because this is a boring, physics thing. They may not be so interested in finding, but once the hands-on come, they are a little more,
There is one comment from somebody.
Yeah.
The part of involving the continuous and pulse wave Doppler was a bit complicated.
Yeah, so continuous wave Doppler is you want to calculate you want to know what is the maximum Doppler shift all along the line of interrogation in the area of interest. So if this is the area of interest, I want to know where is the maximum Doppler shift. That is anywhere in the line the maximum Doppler shift is picked up by the continuous wave Doppler. In pulse wave Doppler, we will know only the, suppose I want to know only at this area and my beam is going like this. So it will give me Doppler shift only at this area, not anywhere. So my maximum Doppler shift will be lying here, 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 anywhere. But I will be calculating only here because I am interested in finding out the velocity here. Because I am calculating here, the exact that there is a limit to which I can measure, and the limit is the Nyquist limit, or which is half of the pulse repetition frequency. So it is actually very complicated. The bottom line is, if we are able to see if you want to measure the velocity at a particular point, you start with pulse wave Doppler, and if you see the signal broken down in two halves, that is aliasing, you increase your scale. If you are not able to optimize the image or get the perfect image in a single plane, it is still broken, then you convert to continuous wave Doppler. I think that should be the message. However, if you are inherently dealing with the flow of blood, which is having a very high velocity, like tricuspid regurgitation, like mitral regurgitation, like pulmonary regurgitation, there is the pulse wave Doppler are useless. You would have to go by continuous wave Doppler. So continuous wave Doppler you use primarily for any regurgitant jets across valves, and the pulse wave Doppler if you want to calculate velocity at a particular point. But if that is not helping, you convert to continuous wave Doppler because of the inherent limitations of